Hi, just to explain the heteronuclear XY molecules interaction diagrams between the orbitals, and we can see here the heteronuclear, if it was X and Y, so they are different in the atom type. So definitely they have differences between electromagnetics for each one of them. So if there is a change in the electromagnetic, it means that they have a change in the energy levels when we put X and Y on the energy level diagram. So there is a fact is less nuclear charge lying higher in energy level, and the higher nuclear charge lying lower at the energy levels. So which one have higher electronegativity will go lower on the interaction diagram, and vice versa. So here we have another fact is saying overlap between orbitals are partly bonding, or in the homonuclear diatoms, same type of atoms, we saw the overlap is complete, is comprehensive. Whereas here in the heteronuclear XY, the overlap is partially bonding and there is partially antibonding. And we can find there is a non-bonding pairs of electrons, non-bonding. So if we come to the shape of PZ, the PZ when interact with the S to give me the sigma bonding, and that's right. So the overlap between the S and one loop here will be partially overlap, but still making the sigma bonding. Whereas the px and s orbital and px and py, they can form non-bonding orbitals. So now, if I come to the electronic diagram, and first I draw the energy arrow that is increased from the bottom to the top, and then I come to the X, which is the first atom has low electronegativity. So the low electronegativity the orbital will be higher than the other Y, which has higher sorry, high electronegative will be lower on the energy level. So now the first time you can see the orbitals will be higher on the energy level for the low electronegative, and the higher electronegative will be lower in the on the energy level scale. And there will be a difference between them, and that is delta E on the energy level. So now in the middle, these orbitals are the combination of this one, like we put like this and this, the combination between this and this. So we'll come to here the bonding sigma, and there is the anti-bonding will be the higher one. So I made it like half from here and half from here, or I can combine the two orbitals from both to be sigma and sigma star. Now we can find as well if they having just S and S, or let's say with the p orbitals, we can find the p orbitals will be in the middle. We put them in the middle, but it's not like 2 by 2. It will be, so if there is a present of p orbitals, the p 3 from here, 3 from here, and then these 3 by 3, they will come in between, in the middle, to become 1, 2, 2, 1. Sorry, it will give you 1, 2, 1, 2. Yeah, 1, 2, 1, 2. And this one belongs to the sigma to the top. So these 3 are belong to the pi orbital. So these are the pi, and here the first one will become the first will be pi, and there is another 2 pi's, and these are the pi stars. So here we have the pi's, and here we have the pi stars. Of course, we talk about there is a presence of non-bonding. So the non-bonding orbitals, whichever they have here from the x and y, you just leave them on the same energy level. So if there is a non-bonding 2 electrons here, if 2 electrons from this y, so they come here as 2 electrons, so they will remain in the same position, same energy level here. And if the other atom has another s or 2 electrons here, so these 2 electrons non-bonding, they will remain as they are non-bonding. So these are the non-bonding. Now let's take an example and see what's happening here. So the example I'm going to take is for the hydrogen fluorine, where there is an interaction between the hydrogen and fluorine. So first we draw the energy arrow that's increasing from the lower to the top. And we come to here to see hydrogen. So the hydrogen, I leave it to the left, and the fluorine to the right. So now the hydrogen has 1 electron in the outer shell. And the fluorine, it has 1s2, 2s2, 2p, it's 9 electrons, 2p5. The halogens have 2p. Okay, so the hydrogen less electronegative. I remember it's 2 point something, 2.5. The fluorine is higher electronegative. So the lower electronegative will go higher in energy. This is the 1s, 1s1. Whereas the orbitals of course, we depend on the 2s2, 2p5 valence electrons. And these 2 valence electrons will be lower than the orbitals of the hydrogen. So I put them as, this is the 2s, 2s2, which they are 2 electrons. And the p electrons, they are 5, 2p, 5 electrons. So the 5, I will put them under the s. These are the 5 electrons, and let me give it a different color. So here I have 1. These are the 5 electrons in the p of the fluorine. Now, now they are ready for combination. So as you see here, these are the 2 electrons. Here I have these electrons belong to the fluorine, whereas this electron belong to the hydrogen. So now if I combine both of them, what will happen? What will happen here is you have the 2s of the fluorine will do no reaction. So they will remain as they are non-bonding. They are in the non-bonding, the 2s. Now we come to the 2p5, and there is one s from here. So the combination, I have 2 pairs of electrons here, 4 electrons in 2 pairs. They will not involve in bonding, so they will remain non-bonding. In the middle, on the same energy level. So I can put them here, 2 by 2. They are non-bonding. But when I come to this electron here, this electron with this electron, this, the single one, it will bond to the hydrogen and they will come here. So I can draw the one from here and the other one is spinning opposite when they form molecular orbital. So here I have a sigma bond. And of course, every time you draw sigma, there is a sigma star. Even it's empty, you have to draw it. So these 2 and 2 came from the same energy level, I left them. But here, this one, with this one, electron formed sigma bonding. This is S PZ. This sigma bond formed by overlapping S with PZ, okay, and forming antibonding. If they get excited, they can go to the higher energy level, to the sigma star. Now, what I been left off, I have 1 pair, 2 pair, 3 pairs. 3 pairs of belong to the fluorine. They didn't involve in the interaction, whereas only 1 electron from the fluorine interacted with the 1 electron from 1s of the hydrogen, and they form single bond. So now, if I now draw the bond order, the bond order is not like we did in the homonuclear. There is a law which are the number of bonding electrons minus antibonding. Here, the bond order of hydrogen and fluorine will be only with the 2 electrons, one from here, and they formed a single bond. What about the others? How can we deal with the other 6 electrons belong to the fluorine? We leave them as lone pairs, 3 lone pairs around the fluorine. So now you have here the single bond, this is the bonding, and these 3 lone pairs non-bonding. 3 pairs, lone pairs, non-bonding. So the bond order here is 1. Now this is the talking about the hydrogen halogen, and we will check the other molecules interact together. We come to the carbon and oxygen. So the carbon and oxygen, if I just come down a little bit. Okay. Now the carbon and oxygen. First, I draw the energy level, and then I come to the carbon to see it has C6, oxygen O8. So the carbon 1s2, here is, I can put the carbon to the left and oxygen to the right. Okay, now this has 1s2, 2s2, 2p2. And the oxygen has the valence electrons 2s2, 2p4. Okay. Okay, so we have here, I have valence electrons 4 in the carbon and I have 6 in the oxygen. So now the first 2s2 I can put here. These are the 2s2 of the oxygen, and I have, because of the carbon is less in electronegative, the orbitals go higher than the oxygen. The oxygen has higher electronegative, so it will come lower in energy on the energy scale for the diagram. So orbitals of the 2s here, let's draw them for the carbon. They are here, 2s for the carbon. The 2s of the oxygen will come lower. So now these two, and then I draw the 3 orbitals of the p, because oxygen is higher electronegative, so it will be lower in the on the energy scale. So 4 and p, these are the p orbitals, 1, 2, 3, 4. I come to the carbon, has 2p2, so 3 energy level higher than p here, and they will come like here, 1, 2. So now here, what will happen for the inter? These are the atomic orbitals of oxygen, atomic orbitals of the carbon. Now we interact them and see what will happen. So the oxygen 2s will involve in no bonding with the carbon. So they will come here as they are non-bonding. These are the non-bonding of the oxygen. So I come to the other 4 electrons of oxygen combined with 2 electrons of carbon. So these 4, the carbon here, the 2s of the carbon will not involve in the reaction and it will remain as non-bonding. So I can put it in the same energy level of the carbon non-bonding. So here is none. Okay, so just for future, just to remember that the carbon Lewis structure, I have to draw them and see that. Don't to forget, there is a lone pair non-bonded from 2s of the oxygen, and there is a non-bonding 2s from the carbon. So now I will deal with the rest. So the 4 electrons in the p with 2 electrons in the p here, they interact together. That's one of the electrons come here and then combine to do a 3 bonding orbitals. So the 3 will come, let's say here, 2 of them, and in pi, one of them making sigma. Okay. And the other 2, 4 electrons will do pi. Every time when you do sigma, it means there is a sigma star. Okay, so 1, 2, 1, 2. And there is here that will do the sigma star. And these 3 will do the pi star. Okay, so now I have 6 electrons here, and the bond order will be 3 because of the 6 electrons. So I have to put the 6 electrons here and draw lines between them. And I can see a triple bond is there. So I have a triple bond, the bond order here, triple for the carbon dioxide, and I have 2 lone pairs, one belong to the oxygen and the other one for the carbon. So as you see now, this is the energy level diagram for the CO, and it is a linear. So this is a linear Lewis structure when there is using dots. Okay, so Thank you for watching.